Good morning, everyone. Today we are going to explore how to move Agentic AI from an interesting prototype into a production-grade enterprise system. The title of this workshop is the Pluggable Agentic AI Framework. The word pluggable is important. We are not proposing that every organization must use one model, one orchestration framework, or one observability platform. Instead, we will introduce an architecture in which individual components can change, while the contracts between those components remain stable. The workshop has two parts. First, we will review the production challenges, design principles, and overall reference architecture. Then we will move into the implementation. We will examine the code, run the multi-agent workflow, inspect its traces, and evaluate its behavior. By the end, the objective is not merely to have seen an agent work. It is to understand what makes an agentic system maintainable, secure, observable, and scalable. Most organizations can now build an agent prototype. A team can connect a foundation model to a prompt, add a few tools, attach a knowledge base, and produce an impressive demonstration in a notebook. But the difficult part begins after the demonstration. Once real users arrive, several questions appear. Can we control what the agent is allowed to do? Can we understand why a response took 8 seconds? Can we identify which model, agent, tool call, or retrieval step caused an error? Can we measure the cost of serving one customer request? Can we change the model provider without rebuilding the orchestration layer? Can we determine whether quality declined after a prompt or model update? These are not simply model questions. They are system questions. The central argument of this workshop is that the gap between a working agent and a production agentic system is primarily an architecture gap. A production agent should be treated as part of a distributed system with contracts, failure boundaries, identity, authorization, telemetry, versioning, and feedback loops. Consider a representative retail example. A team builds a customer support agent. In development, it answers refund policy questions accurately, and the demonstration is successful. 2 weeks after production launch, token spending is 12 times higher than forecast. P95 latency has exceeded 8 seconds. Customer satisfaction has quietly declined by 4 points. Yet no alert has fired. The immediate reaction might be to blame the model. But the deeper problem is architectural. There is no intelligent routing between models. There is no end-to-end trace across agent and tool calls. There is no continuous evaluation loop. Cost and quality are not attributed to individual components. The system produces answers, but the organization cannot explain or govern how those answers are produced. That distinction between generating an answer and operating a system is the focus of this workshop. We can organize the production challenge into 4 lifecycle stages: build, deploy, operate, and scale. During build, teams face framework fragmentation, unclear behavioral requirements, retrieval quality problems, too many tools, poorly scoped memory, and the absence of a meaningful evaluation strategy. During deployment, teams encounter cold starts, environment differences, model serving complexity, permissions, security, model routing, versioning, and rollback. During operation, observability becomes critical. The system may involve several agents, several models, retrieval, databases, and external tools. Traditional application monitoring does not automatically explain this distributed reasoning process. Finally, during scaling, the organization must manage agent discovery, governance, resilience, compute elasticity, compliance, and reuse across teams. These are not 4 independent problem sets. Decisions made during build determine what will be possible during deployment and operation. The cost of an ad hoc approach becomes most visible when an organization builds its second or third use case. Ideally, the first project should establish reusable capabilities, model access, agent registration, memory, security policies, tracing, evaluation, and deployment patterns. The second project should therefore be faster and less expensive. In practice, many organizations see the opposite. Every team selects a different framework. Every agent defines tools differently. Every application creates its own access control logic. Evaluation is improvised for each project. As a result, the platform does not compound. The organization has several agent applications, but it does not yet have an Agentic AI platform. The architecture we will review is intended to create that compounding effect. Before introducing the design principles, we need two definitions. The first is a contract. A contract is a declared and stable interface between components. It might be represented as an API schema, a tool specification, an agent card, or an event definition. The implementation behind a contract can change, but callers should not need to change with it. The second concept is structural. A structural capability is built into every relevant component from the beginning. It is not an optional feature that individual developers may decide to add later. Identity, tool scoping, security controls, tracing, and cost attribution are examples. If only some agents implement them, the overall system cannot reliably claim to be secure or observable. These two concepts, stable contracts and structural capabilities, support the 5 design principles. The reference architecture is based on 5 principles. First, loose coupling through stable layer contracts. Each component exposes a stable interface, while its internal implementation remains replaceable. Second, bounded autonomy. A supervisor routes work, while specialist agents operate within defined responsibilities, tool permissions, data access, and success criteria. Third, discoverability through contracts, not conversations. Agents and tools should be registered with explicit capabilities and schemas. Fourth, security as a structural layer. Agent identity, least privilege tool access, prompt attack detection, sensitive data controls, and policy enforcement should apply consistently across the fleet. Fifth, observability, evaluation, and cost attribution by default. Every interaction should produce structured evidence: which agent ran, which model it used, which tools it called, how many tokens it consumed, how long it took, what it cost, and whether the result met the quality criteria. These principles are not 5 independent recommendations. They form a dependency structure. Loose coupling creates the contracts between components. Bounded autonomy creates the operational boundaries around each agent. Discoverability makes those contracts and boundaries visible and reusable across the organization. Security then enforces policies at those boundaries. Observability measures what happens inside and across them. Finally, evaluation uses that evidence to improve the system. This leads to 2 concise rules. We cannot secure what has no boundary, and we cannot reliably observe what has no contract. If an agent can dynamically use any tool, read any memory, and delegate to any other agent, then guardrails have no stable enforcement surface. Likewise, if calls between components do not follow defined interfaces, telemetry becomes inconsistent and end-to-end evaluation becomes difficult. Together, the principles create 3 important system properties. The first is reliability. Specialist agents become isolated failure domains. If the refund agent fails, the system can report or escalate that failure without necessarily taking down the order agent or the entire customer support experience. The second is evolvability. A model provider, vector database, orchestration framework, or observability backend can be replaced behind a stable contract. The third is elasticity. Different parts of the system can scale independently. A heavily used order agent can scale without scaling every other specialist. These properties are what transform a one-off agent into a reusable enterprise platform. The 5 principles are implemented through 7 architectural layer contracts. These layers are a separation of concerns. They should not be interpreted as 7 products or as a rigid request sequence. Some layers participate directly in request processing. Others, particularly security, observability, and evaluation, operate across the system. The implementation of each layer is pluggable. In this workshop, we will use AWS services and selected partner technologies, but the architectural contract is more durable than any particular product choice. Let us review what each layer is responsible for. Layer 1 is data and knowledge. Its purpose is to give every specialist access to an authoritative world state. That includes unstructured knowledge, such as refund policies, manuals, and product documentation, as well as structured transactional data, such as customers, orders, inventory, and payments. This distinction is important. Memory describes relevant history within or across conversations. The knowledge layer describes facts about the external domain. Layer 2 is model and inference. Different tasks require different levels of intelligence. A simple classification or routing decision may not require the same model as complex policy interpretation. The inference layer allows the system to select the least expensive model that still satisfies the quality requirement. Because the model is accessed through a stable contract, the orchestration layer does not need to be rebuilt whenever the model or inference provider changes. Layer 3 is orchestration. This is where a collection of agents becomes a coordinated system. The workshop uses a supervisor specialist pattern. The supervisor interprets the user's request, determines which capabilities are needed, delegates work to appropriate specialist agents, and assembles the final answer. The specialists execute bounded tasks. They have limited tool sets, declared data access, and explicit success criteria. The orchestration layer also owns the policy for agent memory. Short-term memory supports the current invocation. Session memory maintains continuity for a particular user or conversation. Long-term memory can preserve information across sessions. The important question is not only where memory is stored. It is who may read it, who may write it, how long it is retained, and whether it may be shared between specialists. Layer 4 is security and guardrails. Traditional application security remains necessary, but agentic systems add new risks. A malicious instruction may attempt to override the agent's policy. An agent may be given more authority than its task requires. Retrieved content may contain instructions intended to manipulate downstream behavior. This layer applies controls consistently across agents, identity, authorization, least privilege tool access, prompt injection defenses, topic restrictions, sensitive data masking, and grounding checks. Layer 5 is the application layer. This is the governed surface through which users and other systems consume the agent fleet. It may expose a chat interface, internal APIs, streaming endpoints, MCP-compatible tools, or agent-to-agent compatible agent endpoints. Consumers interact with this managed surface, not directly with the internal implementation of every specialist. Layer 6 is observability. A single user question may produce several model calls, retrieval operations, tool invocations, and agent-to-agent handoffs. We therefore need a correlated trace across the entire interaction. For each step, we want to know the model, tokens, latency, cost, retrieved context, tool result, errors, and responsible agent. Layer 7 is the operational loop. Observability tells us what happened. Evaluation asks whether the outcome was good. Was the response correct? Was it grounded in the policy? Did the system select the correct specialist? Was the refund decision accurate? Did cost or latency exceed its threshold? Evaluation may occur before deployment, during regression testing, or continuously against sampled production traffic. Its results feed changes back into prompts, routing policies, knowledge sources, guardrails, models, and agent definitions. Let us connect the layers through one request. A request first enters through the application layer, where the user is authenticated and the session is established. The supervisor in the orchestration layer interprets the request and discovers the appropriate specialists. Those specialists access models through the inference layer and retrieve authoritative facts through the data and knowledge layer. Security and guardrails enforce policy throughout the interaction, not only at the final response. Observability records every meaningful span: model calls, retrieval, tool use, agent handoffs, latency, tokens, and errors. The operational loop then evaluates the completed interaction and turns the resulting evidence into future improvements. This is not simply a linear pipeline. Security and observability are cross-cutting. Evaluation feeds back into all the other layers. The workshop makes this architecture concrete through any company, a fictional online retailer. A customer logs into a Streamlit chatbot using Amazon Cognito. Cognito returns a JWT containing the customer's identity and service tier. The customer asks, "What's my refund for order ORD10001?" The customer support supervisor receives the request and uses the customer ID as the memory key. It determines that the workflow requires two specialist capabilities. The order agent retrieves the transaction from DynamoDB through the AgentCore gateway. The refund agent retrieves the relevant refund policy from the Bedrock knowledge base, checks eligibility, and invokes the authorized refund operation. The supervisor then applies any customer tier rules, calculates the expected timing, and streams the final response back to the user. Every hop is traced into AWS observability services. On a later visit, the supervisor can use properly scoped memory to preserve relevant customer context. Before moving into the implementation, let us clarify what pluggable does and does not mean. It does mean that a component can be replaced behind a stable contract. We can change an inference provider without changing the supervisor's basic responsibilities. We can substitute an observability platform while retaining the same trace semantics. A partner can strengthen one or more layers without forcing a redesign of every other layer. It does not mean that components can be combined arbitrarily without governance. The contracts, boundaries, identity model, telemetry requirements, and evaluation criteria must remain explicit. The framework also does not require one orchestration technology, one model provider, or one evaluation method. And it does not replace domain-specific evaluation. It supplies the infrastructure into which the relevant business evaluators are connected. We have now established the conceptual model. The business problem is the gap between prototype and production. The design response is a system based on stable contracts, bounded autonomy, discoverability, structural security, and default observability. Those principles are implemented through 7 architectural layers. We will now move from the architecture into the implementation. As we examine the code, I would like you to keep 4 questions in mind. First, where is each agent's responsibility and authority bounded? Second, what contract connects one component to another? Third, what evidence does the system produce when a request runs? And fourth, how do we determine whether the outcome is actually good? We will begin by reviewing the repository structure and configuration. Then we will inspect the supervisor and specialist agents, run the refund workflow, examine the resulting trace, and finally execute the evaluation process. With that context established, let's move into the code. We now move from the architecture overview into the source code. The important point is that we will not treat these notebooks as an unrelated sequence of setup scripts. We will follow the same 7-layer architecture introduced earlier. At each layer, I will highlight 3 things: the responsibility owned by that layer, the contract it exposes to the next layer, and the production concern encoded in the Python. The walkthrough ends with tracing, evaluation, and prompt optimization, so we can see the complete path from infrastructure to a continuously improving agentic system. This is the organizing map for the code. Layer 1 establishes authoritative data. DynamoDB stores the transactional order state, while the refund agent retrieves policy knowledge from a Bedrock knowledge base. Layer 2 creates a stable inference interface. The active model can change without forcing changes in every agent. Layer 3 is the largest section. It creates the registry and gateways, deploys the specialist agents, adds memory, and creates the supervisor harness. Layer 4 intercepts gateway responses and masks sensitive information. Layer 5 authenticates the customer and streams the supervisor response into Streamlit. Layer 6 correlates the distributed work through traces, logs, metrics, latency, and cost. Layer 7 evaluates real sessions and feeds evidence into prompt optimization. So as the code changes files, keep your attention on the layer contract that remains stable. Layer 1 begins with the customer orders DynamoDB table. The create table function is intentionally driven by a JSON definition that keeps the schema separate from the provisioning logic and makes the setup repeatable. The critical design decision is not the create table API call. It is the access pattern. The customer identifier is the partition key, so the order agent can retrieve all orders belonging to one customer. A global secondary index on order ID supports direct lookup of a specific order. Notice the waiter after create table. Cloud infrastructure is asynchronous. Receiving a create response does not mean the table is ready for writes. Waiting for the table exists condition prevents the next cell from racing the control plane. This layer exposes a simple contract upward. Authoritative order records can be queried either by customer or by order identifier. The unstructured half of Layer 1 appears inside the refund agent tool implementation. The query KB function accepts a business question and hides the retrieval mechanics. The agent does not need to understand vector indexes, embeddings, or the Bedrock retrieval response format. The number of results is explicit. Increasing it may improve recall, but it also increases context size, latency, and cost. That makes top K a tunable system parameter rather than an invisible default. The retrieved passages are joined and returned to the refund agent. The important boundary is that the knowledge base supplies policy evidence. The agent interprets that evidence, but should not invent a policy that was not retrieved. This is the first example of the pluggable pattern. The retrieval implementation may change, while the refund policy tool contract remains stable. Layer 2 introduces the inference backend class. This thin wrapper is one of the most important pieces of the design. Every model is called through the same invoke method, and every call returns the same categories of information: content, latency, cost, and token usage. Light LLM handles provider-specific invocation details. The rest of the system does not have to know whether the model is hosted on Bedrock or behind another compatible provider. The interface also makes operational data part of the response contract. Cost and latency are not calculated later from a separate spreadsheet. They are captured at the point where inference occurs. One security issue is present in the source notebook. An API credential is included as a fallback string. I have redacted it from the slide. That credential should be rotated and removed from source immediately. Production code should retrieve it from a managed secret or AgentCore identity credential provider. The backend registry makes the pluggable idea concrete. Each friendly name maps to an inference backend instance. The rest of the workshop reads the selected model identifier from shared configuration, so changing the active backend does not require rewriting agent business logic. However, replaceable does not mean interchangeable without testing. Models can differ in tool calling, instruction following, latency, price, and output structure. The stable interface removes code coupling, but evaluation must still establish whether the replacement meets the required quality threshold. This is why Layer 2 and Layer 7 belong in the same lifecycle. Layer 2 enables substitution. Layer 7 makes substitution safe. Layer 3 begins with shared infrastructure. The registry is a catalog of available specialist agents. The code first lists existing registries and reuses the named registry when it already exists. This create or use pattern makes a notebook safer to rerun. Once specialists register agent cards, the supervisor can search by capability instead of hard-coding every endpoint. Auto-approval is enabled here for workshop speed. In a production environment, registration should normally pass through ownership, security, and capability review. Discoverability is valuable only when the published metadata is trustworthy. The registry contract is simple. A specialist describes what it can do and how it can be invoked. A supervisor discovers it at runtime. The order agent's Lambda tool is deliberately narrow. It supports two inputs: order ID or customer ID. Direct order lookup uses the global secondary index. Customer lookup uses the table partition key. There is no full table scan and no unrelated write capability. This is bounded autonomy at the data access level. Even if the language model produces an unexpected instruction, the order tool still exposes only the permitted operations. The tool also returns an explicit status field that gives the agent a predictable result contract and makes errors observable. The separation of responsibilities is important. The order agent retrieves order facts. It does not decide refund eligibility and it does not process a refund. Those operations belong to a different specialist with different tools and permissions. This slide separates three contracts that are easy to blur together. First, the gateway target exposes the Lambda operation as an NCP tool. That contract connects an agent to a tool. Second, the specialist is deployed as an A2A endpoint on AgentCore runtime. That contract connects one agent to another agent. Third, the agent card is published in the registry. That contract connects a capability search to the correct A2A endpoint. The same pattern is repeated for the refund agent. Because the contracts are explicit, the supervisor does not need to import the specialist's Python code. It discovers and invokes the deployed capability. This is loose coupling in executable form. The refund specialist exposes three tools with progressively greater authority. Refund policy is read-only retrieval. Check eligible is a decision operation. Process refund represents an action with a business side effect. Keeping these separate improves security and evaluation. We can test policy grounding independently from eligibility logic. We can also require stronger authorization before the process refund tool is allowed to run. The current workshop implementation generates a confirmation rather than integrating with a real payment rail. In production, process refund should be idempotent, transactional, auditable, and protected against duplicate execution. This slide shows that tool granularity is not cosmetic. It defines the system's authorization boundaries. The orchestrator harnesses the supervisor. Its system prompt tells the model to search the registry, obtain the specialist runtime address, and invoke the specialist through a second tool. This prevents the supervisor from depending on a locally imported order agent or refund agent implementation. For a refund request, the prompt requires two sources of evidence. The order agent supplies transaction facts. The refund agent supplies policy and eligibility. Date and amount calculations are delegated to the code interpreter rather than performed informally by the model. The prompt is therefore more than tone guidance. It is executable coordination policy. That also means prompt changes are system changes. They should be versioned, regression tested, and evaluated like code. The harness also owns memory policy. AgentCore memory is created with strategies for semantic facts and session summaries. During invocation, runtime session ID identifies the current conversation, while actor ID identifies the customer boundary. Those two identifiers must not be confused. A customer may have several sessions, but memories from one customer must never leak to another actor. The system prompt explicitly tells the supervisor not to invent memories. If relevant retrieved memory is empty, the correct behavior is to say that the information is not on record. Memory is therefore both a capability and a security boundary. Retention, AgentCore scoping, extraction strategy, and access permissions must be treated as orchestration policy. Layer 4 attaches a response interceptor to the gateway. The interceptor checks whether the MCP operation is a tool call. If it is, it walks the response content and sends textual values through a NEMO action that detects and masks personally identifiable information. The architectural advantage is central enforcement. Individual specialist developers do not each need to remember to redact their own output. There is an important risk in the current code. If masking throws an exception, the exception handler returns the original gateway body. That is fail-open behavior. For high-sensitivity environment, the safer policy may be to block the response, return a sanitized error, and alert operations. Guardrail failure behavior is a business decision and should be explicit. Layer 5 begins with authentication. The Streamlit application sends credentials to Cognito, verifies the return JWT signature against the public key, and validates audience and issuer. The customer identifier and service tier are read from verified claims. The customer identifier then becomes the actor ID used by the harness and memory system. The source correctly labels user password authentication as a workshop choice. Enterprise deployment should normally use federated identity, such as an organizational AgentCore SAML provider, and should avoid shared test passwords. The important contract is that the application establishes identity. Downstream agents receive an actor boundary rather than trusting a customer identifier typed into the chat message. The application invokes the harness and reads a stream of typed events. Tool start events are presented as status updates, so the audience can see when the supervisor delegates to a specialist. Text delta events are appended token by token into the chat bubble. Streaming does not reduce model computation time, but it reduces perceived latency and makes a multi-step workflow understandable. The final text is also passed through UI-level redaction. That is useful defense in depth, but it should not be the primary control because data may already have reached logs or intermediate components. The gateway interceptor remains the more structural enforcement point. This layer's job is delivery, identity, session state, streaming, and a governed user experience. Layer 6 follows one request through the distributed system. The tracing notebook queries recent X-ray trace summaries, retrieves the full trace, and flattens segments and subsegments into spans. A single trace may include the harness, registry tool, specialist runtime, gateway, Lambda, DynamoDB, knowledge base, and model calls. The trace ID is the correlation key that joins those hops. The span waterfall answers what happened and in what order. Aggregating span duration by service answers where the time was spent. If model spans dominate, model routing or prompt length may be the optimization target. If Lambda and gateway dominate, Cold starts, connection reuse, or data access may deserve attention. Without correlated tracing, those diagnoses become guesses. Tracing explains an individual request. Metrics summarize system behavior across requests. The observability code queries model token counts, latency, invocations, gateway traffic, and memory activity. These metrics support capacity planning, cost monitoring, and service level objectives. The dashboard notebook also identifies the corresponding log groups. Gateway application logs reveal tool routing and tool responses. Runtime logs reveal startup and invocation problems. The OSPAN's log group supports cross-resource trace search. In production, payload logging must be balanced against privacy. Sensitive request and response content should not be copied into logs without retention, encryption, and access controls. The goal is not to collect every possible signal. It is to connect signals to decisions about reliability, quality, latency, and cost. Layer 7 begins by evaluating real traced sessions. The same session spans are passed to several evaluators. Helpfulness asks whether the response assists the user. Tool selection accuracy asks whether the agent chose the appropriate tool. Correctness asks whether the resulting answer is accurate. These dimensions should remain separate. A fluent answer may be incorrect. A correct answer may have used an unsafe or inefficient trajectory. A tool choice may be reasonable even when the downstream tool fails. The notebook also supports ground truth responses and expected trajectories. Those reference inputs make evaluation stronger, but they must be maintained. A stale expected answer can incorrectly label a properly grounded response as wrong. Evaluation results therefore need explanations and human review, not only a single score. The optimization notebook deliberately generates difficult conversations. The first prompt is ambiguous. The second combines order investigation and refund intent. These are better optimization inputs than easy happy path prompts because they expose weaknesses in routing and multi-agent coordination. Each conversation is fully consumed from the stream, so the workflow completes and its traces are finalized. The optimization service then receives the current system prompt, the relevant session spans, and a quality objective such as goal success rate. It proposes an improved prompt. That proposal should not be deployed automatically. It should enter a controlled experiment. Run the existing and proposed prompts on the same evaluation set. Compare quality, latency, cost, safety, and regression risk, then promote only if the evidence supports it. Let us now replay one refund question across the code. The application authenticates the customer through Cognito, creates a session, and invokes the harness with a verified customer identifier as actor ID. The supervisor searches the registry and invokes the order agent for transaction facts. It invokes the refund agent for policy and eligibility. The refund agent retrieves policy evidence from the knowledge base and uses its bounded decision tools. Gateway responses pass through the NEMO interceptor before returning upward. The harness combines the evidence, uses code execution for exact date or amount calculations, and streams the answer to the UI. At the same time, observability record spans model usage, tool calls, latency, and errors. Evaluation later scores the session, and optimization uses those results to propose an improved prompt. That is the complete architecture expressed as running code. Before the live demonstration, 4 code review findings deserve explicit attention. First, the Pluggable inference notebook contains a hard-coded API credential fallback. Treat that credential as exposed, rotate it, remove it from notebook history, and retrieve future credentials through a managed secret or identity provider. Second, the guardrail exception path fails open by returning the unmasked response. For sensitive workloads, define a fail-closed policy or risk-based fallback. Third, the refund action is a workshop simulation. A real financial side effect needs authorization, idempotency, durable transaction state, audit evidence, and escalation thresholds. Fourth, the Cognito password flow and shared test identities are appropriate only for the workshop. Production should use enterprise federation, short-lived credentials, and least privilege roles. These findings do not change the 7-layer design. They show where the workshop implementation must be hardened before handling real customers or money. We have now connected every major source file to its architectural responsibility. As we move into the live demonstration, do not focus only on whether the chatbot produces a plausible answer. Watch which specialist is selected. Check which tools are invoked and what authority they possess. Verify that order facts come from DynamoDB and policy rules come from the knowledge base. Observe where the response is masked. Then open the trace and identify the critical latency path. Finally, run the evaluators and inspect their explanations before looking at the optimization recommendation. The demonstration is successful only if we can explain not just the final answer, but how the system produced it, what it cost, whether it was safe, and whether it met the quality standard. With that lens in place, let's run the code.